Filtering of a waveform is basically when we take our ripple waveform that we've obtained from the rectifier and we take this bottom level and we shift it up by means of an inductor or a capacitor to convert our waveform into a signal where the high voltage is still the same, but the low voltage, instead of being 0 volts, has moved upwards. We still have a 0 volt level, but that low point on my signal has moved upwards. We do this in one of two methods. The first method is the capacitor filter. The capacitor filter comes from the supply or from the input, which is my ripple, or which has the pulsating DC, and it then connects to my capacitor, which in turn connects to my load. And what occurs now is, if we've got a half wave rectified signal, we have a half wave rectified signal. What happens is that as that voltage increases, I will get an increasing positive negative potential on those 2 points. Those will allow the capacitor to become charged. So during that section over there, the capacitor is going to charge. Once my input voltage decreases, the capacitor is now allowed to discharge through the resistor, which maintains the voltage on the resistor for a longer duration in time. Now remember, time constants, time constant equals the resistor multiplied by the capacitance. Now it takes 5 time constants for this capacitor to completely discharge through the resistor. So what we do is we have a large resistor connected over there, which stores a lot of charge, and then it's just going to take very long for it to discharge. The result is, by the time while that capacitor discharges, we're going to get a signal somewhat like that. Now what happens is, as it discharges, the voltage is going to decrease slowly, but as we get our next pulse introduced, that capacitor is going to start charging again. As a result, the voltage on the resistor does not decrease excessively. With respect to full wave rectification, if we have this exact same value capacitor and exact same load resistance, the effect that that has on the output is, we can see we've got probably about just over 10 degrees over there. So if we look, we see that from the full wave, one pulse to the next, we've got a major decrease of about half of the ripple for the capacitor filter, comparing half and full wave rectification. Half and full wave rectification. Another method that we can apply is the inductor capacitor filter. We can use the inductor on its own. However, the inductor is typically used in conjunction with a filter. Inductor capacitor filter, also called the LC filter. Now what we see with the construction over here, we've got our connection to the input that runs to a inductor, and then from there it splits up into my capacitor line as well as my load line. Now if we look at the inductor on its own, remember it has the ability to delay the flow of current due to the inductive reactance it's going to get because of the frequency it experiences, and the capacitor will store a charge for later use. So what we get is, for half-wave rectification, this circuit is not commonly used. Typically use it for full wave rectification. So what we get going in, this is across the inductor. What it does is, this is the voltage that it is experiencing, and as a result this is the current that it is going to push through the resistor. We can see there's a clear 90-degree phase shift between the voltage and the current. There's my current, there's my voltage. Voltage leading by 90 degrees if we think back to the RLC circuits. So the inductor allows current to be delayed by 90 degrees. So that is the current that's going to flow through the resistor only because of the inductor. But now if we add the capacitor concept to this as well, also these two are going to attempt to resonate, and as a result that current is also experienced by the capacitor, which allows the inductor or the capacitor to charge according to that current, and as a result our filter that we're going to get is going to be still there, but it is going to be more sinusoidal, and it is going to be a lot smaller ripple compared to just the normal capacitor filter. The downside with the inductor capacitor filter is the inductor typically takes up a whole lot of space on the PC board. It generates magnetic fields which could cause interference with components and circuitry around it. Because of the size and the weight of the inductor, these circuits are typically very heavy, and as a result, also because of the construction expenses of the inductor, those circuits or those components tend to be very expensive.